In our last few lectures, we have talked about partial differential equations. In particular, we have talked about one-dimensional transient diffusion equation. We have solved the equation, we have seen several techniques to solve it, and we have seen the stability consistency of such schemes. Now, in this lecture, we'll look at the heat transfer in a nuclear fuel rod. Now, don't get intimidated with this title. We are not going to go any detail of this problem. What we'll do, we'll develop a very simple model of this nuclear rod, a heat conduction model of nuclear rod. You will see that it will be steady state conduction with heat generation, and then we'll try to solve this model and see what we can learn. So let us just revise our heat conduction. The governing equation of heat conduction turns out to be del T rho Ct. This is the internal energy part. This is the heat that is stored in my system. Rho is the density, C is the specific heat. So this is mass, specific heats, and temperature. This is how heat is being stored. On right hand side, there are two terms. First one is the heat transfer due to diffusion or conduction heat transfer, and then there is a heat generation term if anything happens and heat generates within the system. If the material properties are constant, then this density, specific heat, thermoconductivity, we can take them out and the equation looks slightly simpler like this. Here this del square is the Laplacian, and it gives us this del square del x2, del square del y2, del square del z2, etc., etc. in 3D Cartesian coordinate. If we consider 2D Cartesian, then the third term del 2 del z2 will go out, only the first two terms will remain. If we consider one dimension, then the second term will go out, but let us stick to this. Let us stick to this 2D Cartesian. In steady state conduction, we know that this time derivative will be 0. Since time derivative is 0, we can take this right hand side k del square t plus q triple prime to be 0. Or we can write this del 2t is equal to minus q triple prime by k. This is a very famous equation. This type of equation is very famous, known as Poisson's equation. And we'll focus next few lectures as well as this lecture on this equation. So in case of a two-dimensional steady conduction, I can expand this Laplacian as we have already stated here, and I write this 2D steady state heat conduction equation del 2t del x2 plus del 2t del y2 is equal to minus q triple prime by k. So I did not neglect the generation. Generation is still here. This type of problems usually comes with three types of boundary condition. There could be more, but these three are more common. First one, we already know. We have already used this kind of condition, which we call Dirichlet type condition, where the temperature or the unknown that we are calculating for, that is specified at the boundary. So for instance, T equals certain T infinity is known. So then this is Dirichlet boundary condition. The second type of boundary condition is Neumann boundary condition, where the gradient of temperature is specified at the boundary. Now we know that gradient of temperature is related to heat flux. So for instance, this Fourier's law, it states that minus k del t del x is equals q in x direction. So this is the heat flux. So when gradient is specified, that means that the heat flux is specified. And in special case, when this gradient is 0, that says heat flux is 0. And having 0 heat flux means that surface is insulated or maybe symmetric. We'll see that symmetry problem later on. but mathematically they mean very similar thing, this symmetry as well as insulated condition. Now, the third condition is the Robin condition. In Robin condition, we have A del T del X plus BT equals C, where this A, B, C are constant. On Y direction, it could take A del T del Y plus BT equals C. This is a convective type condition, and we'll see in convection how this comes. In general, in Robin condition, A and B, they are not equal to 0. But if any of them are 0, for instance, if A is 0, then Robin condition goes toward this Dirichlet condition because this derivative term will go away. Similarly, if B is 0, then Robin condition will go toward Neumann type condition because this BT will go away. So now with this background, let us approach this fuel rod problem. The schematic what you see here, this is a nuclear plant. This is actually molten sodium cooled plant. Now you may be already aware about it from other courses, or you may not know about it at all. That really doesn't matter now. This problem we are setting only as a background, but we'll quickly leave the nuclear plant and we'll get into the model. So here the heat is being generated within this fissile core, this red portion here in the reactor. And because of nuclear reaction there in the fissile core, heat is being generated. Then that heat is being transported by molten sodium in this case, and through several heat exchanger, finally that heat is used to heat water and make steam. These two are similar system, but design wise, in left side here loop design, the heat exchanger is outside the reactor, and in pool design it is inside the reactor. But we are not really concerned about it. Once that heat is transferred to the water, it makes steam, and the steam turbine runs using that steam, and electricity is generated from turbo generator. But what we are concerned about is this fuel rod. This fuel rod is generating heat due to nuclear reaction, and we are not going to model nuclear reaction. That is not in the scope of our study. What we will assume that heat conduction is going on in the fuel rod, and heat is being generated inside the fuel rod uniformly, and then this hot fuel rod is transferring the heat to outside fluid which is colder than the rod. These fuel rods are usually long, so we will not look at the entire fuel rod. Rather, what we will do that we will take a complete rod, a cross section, and we will look at only at this section. We assume this section is like square. So our assumption is that in this direction the change in temperature is not that much. Mostly it is happening here. The gradients are happening at the cross section. Outside this rod there is convective heat transfer. Due to convective heat transfer H, there will be convection. This is what we are going to model. And just like any thermal power plant, this plant also, it operates primarily on steady state. So it's a alright assumption to assume steady state. This control rods actually make sure that the plant will operate at steady state, but let us not go deep into it. So essentially the problem comes down to be a two-dimensional steady state heat conduction where convection is happening at the boundary. So let us see how can we model that. So here this is the cross section of our fuel rod. It has an uniform volumetric heat generation rate, that is Q triple prime, and then the heat is lost to outside fluid due to convective heat transfer. Outside fluid temperature is T infinity, and H is the convective heat transfer coefficient that is known to us. Therefore, the convective heat flux will be given by H multiplied by this T, that is the surface temperature here, minus T infinity. Generation inside and convection to outside, together they are balancing it. Therefore, the system still remains at steady state, which means that temperature at any point will not change in time. Under such condition, we take this rod and make a mathematical model out of it. In our model, the rod goes from -L to +L in both x and y direction. The governing equation is this Laplacian of t is equal to minus q triple prime by k, which we have already established. We'll solve this equation, but before that we have a long way to go. First, of course, we have to specify boundary conditions, but even before that, I'll non-dimensionalize this equation. So let's begin with the non-dimensionalization of distance, that is x and y, and I define this dimensionless distance x star is equal to x divided by L and y star is equal to y divided by L. And let us go with this for now before doing anything with the temperature or other variables. With this definition, we can write this del x is equal to L del x star, del y equals L del y star. And now I want to plug them in the equation. Once I put them, this del x square will now become L square del x2, L square del y2, L square, we cannot cancel L square, so L square can simply go other side. So now my equation is like this. It's look very similar to the equation we had before. X is replaced by x star, y is replaced by y star. The generation part which was there on the right side, now it is more even complicated. I have an additional term there. T is dimensional, it is not non-dimensionalized yet, but you can see that in this side, I have this q triple prime L square by k. So if I divide t by this term, immediately the equation will be dimensionless. We'll do so, but even before that, we'll just want to see that my t, how bigger or how closer it is than t infinity. That will give us a very good physical information. Therefore, what I define here is theta is t minus t infinity divided by this right hand side term, positive part of that, q triple prime L square by k. With this definition, you can see that I have this del t is del theta divided by q triple prime L square by k, etc., etc. So with such definition of theta, we have our dimensionless equation, that is del 2 theta del x star 2 del 2 theta del y star 2 equals -1. It looks now much better. We have removed this q triple prime by k. In fact, we have consumed it within our new definition of temperature. So now on the right hand side, I only have -1. So we are good to go, but before we do anything, we have to first specify and then non-dimensionalize the boundary conditions as well. So to go about boundary condition, we'll very carefully develop the boundary condition by carrying out an energy balance at the boundary. So let us just assume that this is our computational domain, this box, and this is, let us say, one of my boundary, maybe x equals 1. Outside, I have temperature T infinity, which is a constant, and a convective heat transfer coefficient H, which is also constant. The boundary itself is actually an imaginary surface. It has zero thickness, but it is difficult to assume something with zero thickness and do some balance over there. So what we do, we sort of enlarge our boundary. We put a lens over this boundary such that our boundary now look pretty thick. So you can now say that my boundary is like a volume now. All right, so then what is happening within this volume? In this volume, I am drawing this unit vectors over this area, n1 and n2. Unit vectors will always go outside from the volume. Using that convention, both unit vectors are going outside. Now we have to see the heat fluxes at the boundary. This Q1 is the heat flux that is coming from inside, and Q2 is the heat flux that is coming from surroundings. So you may be wondering that nothing is coming from surrounding. It is actually heat is being lost to surroundings. But mathematically they are same, because then in that sense Q2 will only become negative. So we'll go with this. Now this box here, heat is coming from inside, heat is coming from outside, and this box is storing heat. But then this box can store heat only if the box has certain mass, certain volume. Then it can store heat as this mass into specific heat as volume. So in unit into temperature, so in unit volume it will store then rho Ct. But it doesn't have any mass. So in the limit that this has no mass, this is just an imaginary surface, it cannot store energy, which means that all the heat which is coming there together, their sum will be zero. It will not change anything. Or in other word, all the heat that is coming in is equal to all the heat that is going out. Q dot n dA equals 0. So this Q dot n Q1 is at this N1 surface. Q dot n gives as much as Q is coming from this direction. So Q dot n dA, Q and N, you can see that Q1 and N1 there in opposing direction, which means Q dot n will be minus Q1. Similarly, Q2, N2, it will be minus Q2. This will be 0 because area is same for both, so area cancels out. So the boundary condition becomes minus Q1 minus Q2, 0. Now what is minus Q1? Q1 is coming from Fourier's law. We know that Q1 is minus K del T del X. So minus Q1 is K del T del X. Similarly, Q2 is the convective part. So my Q2 is coming from outside. So my Q2 will be given by H T infinity minus T, because it is coming from outside. Outside temperature is T infinity, surface temperature is T. So if this is my Q2, then minus Q2 will be H T minus T infinity. This is my boundary condition. You can see that this is Robin type boundary condition or convective boundary condition. We non-dimensionalize it with already defined x star, y star and theta. If I do this, you will see that this Q triple prime L square K will go away because both has T. So other side is 0. So what we will have is this K del theta del x star, but there is an L coming here, H theta. So now this H, K and L, I can club them together and I can write that as Bi, which is known as BO number H L by K. This is a very, very important dimensionless number in heat conduction. But if you know it, that's fine. If you don't know it, don't bother about it. For our problem, we will treat this as a constant and we will solve our problem. So now we have dimensionless boundary condition. But then this is only one boundary condition. I have several other boundaries. And there you can carry out an energy balance just like this. I'll not go through the detail. I'll only show you that what is the boundary condition in any other boundary. So what will happen is like this. You will see that in all boundary, the boundary conditions will be similar. In X boundary, it will be del theta del X star plus Bi theta equals 0. In Y boundary, del theta del Y star plus Bi theta equals 0. And my solution domain goes from this XYL to XY minus L. So XY star 1 to XY star minus 1. So this is my X star 1, X star minus 1, right side and left side. Similarly, here my top and bottom are Y star 1, Y star minus 1 respectively. Within this solution domain, we are now ready to solve the problem. We have to know certain value of bi, and that's it. We can solve the problem. This is the only parameter now. We have reduced all the parameters through non-dimensionalization. But even before we go, can we simplify this problem any further? Well, one thing you can see that it looks like, looking at the boundary condition as well as the governing equation as well as the geometry, it looks like that it's very symmetric. So for example, I can cut the domain half here, and the same thing should happen on the top and bottom. So we can cut the domain half in, let us say, against y-axis. You can see that this is symmetric in positive y, negative y. If we solve in positive y part, then negative y should be a mirror image of that. But then if it is so, if we can assume that, why we stop there? We should actually cut this even half in other direction. For instance, we can cut in x direction, so we can take this out, and then what happens that only this part, that is 1/4 of our initial domain, that will remain here, and we can solve here. So now my domain goes from x equals y equals 0 to 1, and I can solve here. So 1/4 of the original we are solving. It will reduce at least 1/4 of the computational cost. But the problem there is that we do not have boundary conditions really. We have boundary conditions here, but we do not have boundary conditions here. So what we are going to do about it? So now let us look at the problem. We have used symmetry and we are solving in 1/4 of domain. That's the good news. The bad news is that we don't have boundary conditions here. At x equals 1, I have boundary condition. I have established boundary condition, that is convective. Y equals 1 also I have established boundary condition, that is convective. Now because this is symmetric, and whatever happens, for example, on the right side, the same things will happen on the left side. It is just a mirror image. And what I can write is that here at this boundary, the symmetry tells us that this gradient will be 0. So for example, if temperature is dropping like this here, temperature should drop like this here also. Therefore here at this point, this is, you look at right side or left side, you look at the same thing. Therefore we can use symmetry argument, and we say that del theta del x will be 0 here. Similarly, on the other boundary, we use symmetry argument, and we say del theta del y equals 0 here. So now our formulation is complete, but just taking from a Q, let me give you a caveat. Don't use this all the time. You have to be carefully look into it that will there be symmetry. Symmetry condition is restricted to linear problems only, and this is indeed a linear problem. So you have to have geometric symmetry, boundary condition symmetry, and then the overall problem must be a linear problem. Then only you can have symmetry. Now let us summarize this part of our study. We have modeled the heat transfer in a nuclear fuel rod in a very simplistic manner. This is a two-dimensional steady state heat conduction with internal heat generation. You can now forget about the nuclear rod problem and focus on only the mathematical problem at your hand. For your exercise, you think about it, that is this problem solvable by using separation of variable. You go back and see the separation of variable lecture and comment from there. So that's all for this lecture. Thank you, and I'll see you in next class.